Welcome back to week 4 of pre-calculus. Last time we talked about polynomial division, and today we get to apply what we learned last time. We talk about zeros of polynomial functions. In this first part of this conversation, we will go over 3 important theorems. The first of them is the remainder theorem, which states the following. If you divide the polynomial f by a linear polynomial x minus k, where k is a real number, with remainder, then the remainder is exactly the value of that polynomial f at that number k. Let us explain why this theorem holds. Well, when we divide our polynomial f by x minus k with remainder, we learned last time that there exist unique polynomials q quotient and r remainder, for which we have f equals quotient times divisor plus remainder. Since the degree of the polynomial x minus k, which is the divisor, is 1, the degree of the remainder must necessarily be less than 1, or the remainder must be 0. If the remainder is not 0, its degree being less than 1, must be 0, and so the remainder must be a constant polynomial. The only polynomials of degree 0 are constant polynomials. I can write r of x equals r to signify that the polynomial r does not really depend on the variable x. If we now substitute x for k in this equation, k minus k naturally is 0, so this entire term is 0. We immediately get that f at k equals r. Remainder equals the value of our dividend polynomial computed at that point k. This theorem may be applied to evaluate polynomials at points, because if you need to compute a polynomial at a certain point, for instance, compute the value of this polynomial at the point 2, all you really need to do is divide that polynomial by x minus 2 with remainder, and whatever the remainder is will be the value of f at 2. This is not faster than computing f at 2 directly, but it's usually easier. So let us demonstrate how this works. Again, in this example, we evaluate the polynomial f, which is 6x to the 4th power minus x cubed minus 15x squared plus 2x minus 7 at the point 2. Rather than directly plugging 2 into this polynomial, we choose to divide the polynomial by x minus 2, and by the remainder theorem, the remainder in this division will be exactly the value of that polynomial at 2. identifying the leading terms of the dividend and the divisor, we see that we are dividing 6x to the fourth over x, and of course the quotient is 6x cubed. And now the quotient 6x cubed is multiplied by the divisor x minus 2. It will be 6x to the fourth minus 12x cubed. The difference is 11x cubed minus 15x squared plus 2x minus 7. The degree of the remainder is still greater than the degree of the divisor, so the process continues. The leading term of the remainder, which is the new dividend, is 11x cubed. And so we're dividing 11x cubed over x, and that'll be 11x squared. That'll be the next term in the quotient. Multiplying 11x squared by x minus 2, we get 11x cubed minus 22x squared. The difference is 7x squared plus 2x minus 7. The degree of the remainder is 2, which is not less than the degree of the divisor, which is 1. So the process continues again. The leading term of the new dividend is 7x squared. We divide this by the leading term of the divisor, which is x. That'll be 7x. So 7x is the next term in the quotient. And now we multiply 7x by x minus 2 to get 7x squared minus 14x. The difference is 16x minus 7. The degree of the remainder is 1, which is no less than the degree of the divisor, which is also 1. So the process continues. We divide 16x as the leading term of the dividend by x, which is the leading term of the divisor. So 16 will be the next and the last term in the quotient. And now multiplying 16 by x minus 2, we get 16x minus 32. And the difference is 25. The process now terminates because the degree of the remainder, being a constant polynomial, is 0, and it's less than the degree of the divisor. And this last remainder (25) is exactly the value of our polynomial f at the point 2. All right, that was the remainder theorem. The next important result is the factor theorem. Which states the following. A real number k is a zero or root of the polynomial f if and only if the linear polynomial x minus k is a factor of f, meaning that f can be written as x minus k times some other polynomial g. And again, it's easy to explain why this theorem holds. By the remainder theorem, when we divide our polynomial f by x minus k, we again get a representation like this, where remainder r is a polynomial of degree 0, because the degree of the remainder must be less than the degree of the divisor, and the degree of the divisor is 1, so the degree of the remainder must be 0. So r of x is really constant r. And if k is a root of f, it means that f of k is 0. And substituting here x for k, we immediately get this whole term 0, and so it follows that r equals 0. R equals 0. Now, because r equals 0, we have f of x equals x minus k times q of x. And we can take our polynomial g that the theorem talks about to be q. So we have explained that if k is a 0 of f may be written as x minus k times another polynomial. The converse is also easy to explain. If f can be written in this form, x minus k times another polynomial, then of course f at k is 0, because when you substitute x for k on the right, you get k minus k as a factor, and that is 0. All right. In this case, when x minus k is a factor of f, we will also say that x minus k divides f. In example 5, we are asked to show that x plus 2 is a factor of this cubic polynomial. Then we need to find the remaining factors and use these factors to determine the zeros of this polynomial. Now let's start with the first question. Show that x plus 2 is a factor of this cubic polynomial. This could be done in two ways. One way would be to directly divide this cubic polynomial by x plus 2 and verify that the remainder is 0. Another way is to directly plug x minus 2, x equals minus 2, into the polynomial. We will go with the first way, simply because we have other questions to answer. And we need to divide this polynomial by x plus 2 to get the quotient to find the remaining factors. So let me do the division on the next page. X cubed minus 6x squared minus x plus 30 is divided with remainder by x plus 2. The leading terms are x cubed and x. Their quotient is x squared. Multiplying back, we get x cubed plus 2x squared. The difference is negative x squared minus x plus 30. The leading term is negative 8x squared. The ratio of the leading terms is negative x, negative 8x. Multiplying back, we get negative 8x squared, negative 16x. The difference is now 15x plus 30. The ratio of the leading terms is 15. Multiplying back, we get 15x plus 30. The remainder is 0. And so, indeed, our polynomial x cubed minus 6x squared minus x plus 30 can be written as x plus 2 times x squared minus 8x plus 15. And now it's easy to find the other factors, because factoring out this quadratic polynomial is no problem. It factors as x minus 3, x minus 5. Therefore, the zeros of the polynomial x cubed minus 6x squared minus x plus 30 are negative 2, 3, and 5. All right. The third theorem I'd like to tell you about is the so-called rational root theorem. Let us first make a convention about rational numbers, which, as you remember, are numbers of the form m over n, where m is an integer and n is a positive integer. So we agreed to write rational numbers, fractions, always in lowest terms. So for instance, we will never write negative 4 over x, because 4 and 6 share a divisor other than 1. We can reduce this fraction and write it as negative 2/3. Now 2 and 3 are co-prime, they don't share any divisors except 1, and this is a fraction written in lowest terms. We agree to write all our fractions in lowest terms when we talk about rational numbers. With this convention in place, we obtain the uniqueness of representation of rational numbers. There is one and only one way to write every rational number in the form m over n. For instance, to write 0, you use the fraction 0 over 1. You can't use 0 over 2 because that's not in lowest terms. 0 and 2 share a divisor other than 1. This fraction could be reduced by 2. All right, now the theorem itself. Suppose we have a polynomial, and this time we write it in full with coefficients, with a sub n being the leading coefficient, a sub 0 being the free term. And suppose that the coefficients a sub 0, a sub 1, up to a sub n are integers. Suppose also that the rational number p divided by q, written in lowest terms, meaning that p and q are integers sharing no divisor other than 1. So the two assumptions are that the coefficients of the polynomial are integers and that it has a rational root, p over q, where p over q is written in lowest terms. Then the denominator of this fraction, q, divides the leading coefficient a sub n, and the numerator of that fraction, p, divides the free term a sub 0. In particular, if the leading coefficient a sub n is 1, q dividing the leading coefficient being 1 implies that q is 1, and so p over q equals p, and we get that our polynomial must have an integer root dividing the free term a sub 0. Now this theorem has a great practical value because in many situations the coefficients a sub n and a sub 0 are relatively small numbers, and it's easy to check all of the divisors of a sub n and a sub 0, and in hope to find a rational root, we may form all possible ratios p over q, where p divides the free term and q divides the leading coefficient, and check them one by one. Let me show you two examples where we do exactly that. We will use the rational root theorem to find all the zeros of these two polynomials. One is a cubic, the other polynomial is of degree 4. Note that this generally is a difficult task. There are no formulas that we could use in practice to find roots of high degree polynomials, although there are formulas for the roots of polynomials of degree 3 and 4. They are not very practical. We will not use them. We will use the rational root theorem. All right, so let me move to the next page. And the polynomial in part A was 2x cubed plus x squared minus 4x plus 1. And by the rational root theorem, if there exists a rational root, p over q, with p and q integers, q not 0, then the denominator q must divide the leading coefficient 2, and the numerator p must divide the free term 1. This vertical bar symbol here means divides. We will write A vertical bar B to mean that A divides B. Or in other words, when B is divided by A with remainder, the remainder is 0. All right. What can we say about P and Q knowing that P divides 1 and Q divides 2? Well, the only numbers dividing 1 are 1 and -1. So it follows that P is either 1 or -1. Likewise, the only numbers dividing Q are ±1 or ±2. So we need to form all fractions P over Q where P is ±1 and Q is ±1 or ±2. When we form all such fractions, we understand that P over Q belongs to the set ±1 and ±1/2. Unfortunately, at this point, you have to check all these roots. You have to keep on checking all these roots until you find one that works. And remember that the existence of a rational root is not guaranteed. The theorem does not say that a rational root must exist. It only says that if one exists, if a rational root exists, its numerator and denominator must have these interesting properties. But in our situation, we quickly find that 1 is a root, because if we compute f at 1, we see that f at 1 is 0, and therefore x equals 1 is a root. Now, by the factor theorem, x being a root implies that x minus 1 is a factor of f. In other words, x minus 1 divides f. So we divide our polynomial by x minus 1 with remainder. Two x cubed plus x squared minus 4x plus 1 by x minus 1. The leading terms are 2x cubed and x. The ratio is 2x squared. Multiplying back, we get 2x cubed minus 2x squared. The difference is 3x squared minus 4x plus 1. The leading term is 3x squared. The ratio is 3x. Multiplying back gives us 3x squared minus 3x. The difference is negative x plus 1. Negative x is the leading term. The ratio of the leading terms is negative 1. Multiplying back, we get negative x plus 1. And as expected, the remainder is 0. If it didn't come out 0, we would have known that something somewhere must have gone wrong. We knew that the remainder would be 0. So this division shows that our polynomial 2x cubed plus x squared minus 4x plus 1 equals x plus 1 times 2x squared plus 3x minus 1. And to find all the other roots of this polynomial, all we need to do is to find the roots of this quadratic polynomial for which we can use the known formula. The roots are -3 plus minus square root of 3 squared minus 4 times 2 times -1 over 2 times 2. That is -3 plus minus square root of 17 over 4. And we see immediately that 1 is the only rational root. So we can write the answer. The roots of f are 1, -3 minus square root of 17 over 4, and -3 plus square root of 17 over 4. And in part B of this problem, we have the polynomial 8x to the 4th plus 26x cubed plus 39x squared plus 26x plus 6. And again, by the rational root theorem, if a rational root P over Q exists, then the denominator Q must be a divisor of 8, and the numerator P must be a divisor of the free term 6. Q dividing 8 implies that Q is either plus minus 1 or plus minus 2 or plus minus 4 or plus minus 8. And P dividing 6 implies that P is plus minus 1 or plus minus 2 or plus minus 3 or plus minus 6. Therefore, the ratio P divided by Q is one of the following numbers: plus minus 1, plus minus 2, plus minus 3, plus minus 6. It's when you divide all of these by 1. Now, when you divide all of these by 2, you will get plus minus 1 half. 2 by 2 is 1, which we already have. 3 by 2 gives us plus minus 3 halves. 6 by 2 gives us 3, which we already have. Now, dividing 3 by all of these numbers gives us 3, which we already have. 3/2, which we already have. Now 3/4 and 3/8. How about 6? 6 by 1 is 6, which we have. 6 by 2 is 3, which we already have. 6 by 4 is 3/2, which we already have. 6 by 4 is 3/4, which we already have. This is a pretty long list, and there is no way to say if any of these numbers will work, and if any of them will work, which one would that be? So we have to keep on checking them one by one until we find such numbers. In fact, you can check that -1/2 and -3/4 work. That, by the factor theorem, implies that x plus 1/2 and x plus 3/4 are factors of f. And therefore, the product of x plus 1/2 and x plus 3/4 is also a factor of f. So the plan is now this. We will divide our polynomial f by the product of x plus 1/2 by x plus 3/4. Whatever the quotient will be, the zeros of the quotient, if any, will be the zeros of f. And f will not have any other zeros. -1/2, -3/4, and whatever zeros the quotient will have. Now, rather than dividing f by the product x plus 1/2, x plus 3/4, which is f over x squared plus five quarters x plus 3/8, I'd rather divide 8 times f over 8 times the divisor. By doing that, we get rid of the fractions. So we're dividing 8 times f over the polynomial x squared plus 5x plus 3. Now 8 times f will be 64 x to the fourth plus 26 times 8 is 160 by plus 48 is 208 x cubed plus 39 times 8. That's 240 plus 72. 312. times x squared plus again 208x plus 6 times 8, which is 48, by x squared plus 5x plus 3. The leading terms are 64x to the fourth and x squared. The ratio is 64x squared multiplying I made a mistake when I was distributing this 8. The divisor should have coefficient 8 in front of x squared. Now the ratio of the leading terms is 8x squared. Multiplying back, we have 64x to the fourth Oh, I totally incorrectly distributed the 8. One more time. 8 times x squared, 8 times 5 quarters. That's 10. And here we have 3. Eight x squared times 8x squared gives us 64x to the fourth. 8 times x squared times 10x gives us 80x cubed. And 8x squared times 3 gives us 24x squared. The difference is 208 minus 80 is 128x cubed. 312 minus 24 is 288x squared plus 208x plus 48. Now the ratio of the leading terms is 128 by 8 is 16. X cubed over x squared is x. So 16x. Multiplying back, we have 128x cubed plus 160x squared plus 48x. Now the difference is 288 minus 160 is 128. 208 minus 48 is 160. Now the ratio of the leading terms is again 16. Multiplying back, we get 128x squared plus 160x plus 48. And the remainder is 0. So what our computation shows is that the ratio of f and the product of x plus 1/2 by x plus 3/4 is this polynomial. Our polynomial f being 8x to the fourth power plus 26x cubed plus 39x squared plus 26x plus 16 equals x plus 1/2 times x plus 3/4 times 8x squared plus 16x plus 16. We can write it in a nicer way if we factor out 8 and write 8 as 2 times 4. It'll be 2 times x plus 1/2, 4 times x plus 3/4, and here I have x squared plus 2x plus 2. So that'll be 2x plus 1, 4x plus 3, x squared plus 2x plus 2. So if f has zeros other than -1/2 and -3/4, those zeros must be the zeros of this quadratic polynomial x squared plus 2x plus 2. So what's left to do is to see if there are any roots of this polynomial. But we see this polynomial has no real roots. This is because the discriminant d is 2 squared minus 4 times 1 times 2, and that's negative. So the only roots of f the only real roots of f are -1/2 and -3/4. And one more time, I'd like to emphasize that the rational root theorem does not guarantee the existence of a rational root. It only says that if that root exists, which it might not, then it has certain interesting properties. Consider, for instance, the polynomial x squared minus 2, which factors as x minus square root 2, x plus square root 2. Certainly it has roots. Those are plus minus square root 2, but neither of the roots is a rational number. If you didn't know how to find them, the rational root theorem wouldn't help you. The rational root theorem only works when it's known that a rational root exists. So in these examples, we didn't know that a rational root existed. Rather, we hoped that one exists. And if it did exist, it would have been possible to find it using the rational root theorem. And indeed, in both cases, rational roots did exist, and we found them using the rational root theorem. All right, this is it for today. We will talk about zeros of polynomial functions and factorization theorem next time. Thank you.